Okay, we're going to start using different convergence tests to determine what series converge. Right now we have two series that we know how to find the sums of. We have the geometric series, and that's the one that is added up as 1 over 1 minus, that's a minus r equals the sum k equals 0 to infinity of r to the k. And we have to have, for this to work, r has to be strictly between -1 and 1. And then another type is we have a telescoping series. I can't write the exact formula like I can for the geometric series, but basically they look something like this. It doesn't even matter where it starts. Since it doesn't matter where it starts, I know it'll end at infinity. It'll look something like this. These are the ones where you break up the fraction using partial fractions, and there's a bunch of canceling. Then you look at the limit as n goes to infinity. N would be up here if I was going to put it. So these are the two types of series that we know how to find the sums for. For the rest of the series, we don't have formulas most of the time. We'll develop formulas for a whole class of things later on, but right now we don't have formulas. So the best we can do is try to determine when a series converges. And that was the gist of what I did in the previous video that was theoretical in nature. It's optional, but I think it's quite educational if you give it a try. Let me sort of write what the gist of that thing said. Let Sn, n equals 1 to infinity, be so what that means is that we know that Sn is strictly less than Sn plus 1 for every n. Now, if there is a bound, let's say m, for every s sub n. And what does that mean? That means that s sub n is less than or equal to m for all n. And in fact, it doesn't have to be true for all n. It just has to be true for an n at some point on. But if it's true for n at some point on, the first n minus 1 terms are bounded anyways because they're just terms. So we can say something like this. I can adjust this m to make sure that it counts for every single one of them, assuming that there is an m that bounds the last so many of them, if that makes any sense. So if there's a bound, okay, then by the least upper bound axiom, that one is not traditionally spoken much of until we get to this section, but a lot of details or a lot of theories avoided to try to get through the results and get to working problems. So by the least upper bound axiom, the limit as n goes to infinity, s sub n, is guaranteed to exist. So, and in fact, if you choose the right m, say the m happens to be the least upper bound of all the Sn's, well, that happens also to be the limit of this thing. So many times, though, we don't actually know what the least upper bound is. All we know is that the thing is limited. Let me give you an example of what I'm talking about. I know that 1 over k squared is a convergent series. Okay, then is 1 over k cubed also convergent? Well, take a look now. If k is any whole number, say these start at 1, so let me go k equals 1 to infinity, k equals 1 to infinity. Well, it's true, isn't it true, that k squared is less than or equal to k cubed for every k? Since that's true, and they're positive too, I'm talking about k being 1 to infinity, k is always a positive number. That means that 1 over k cubed is less than or equal to 1 over k squared for every k. But then the sum from k equals 1 to infinity, 1 over k cubed is less than or equal to the sum k equals 1 to infinity, 1 over k squared. Since this exists, I'll put something like this in front of it, after it. This forces, since this exists, that means that this also has to exist, because I'll show you why. I think I'm going to do note. You don't have to know this, but I'm just going to write it here for future reference. The proof of this is kind of hilarious. It's definitely not safe for Calc 1 Calc 2 students. Even Calc 3, it's a funny argument, but I'll nonetheless put it here. Believe it or not, that equals pi squared over 6. You don't have to memorize that. I just want you to know. So we could, if S sub n is the sum from k equals 1 to n of the series 1 over k cubed, then Sn is definitely less than Sn plus 1 for every n. Okay? So Sn is an increasing sequence. Not just increasing, it's an increasing sequence of positive numbers. So Sn is an increasing sequence which is bounded by pi squared over 6. Since this series is less than this series, less than or equal to this series, that means that this series, no matter what n is always going to be less than, probably less than this, but I'll put less than or equal to just to be on the safe side. So I have an increasing sequence bounded by pi squared over 6. This implies that the limit as n goes to infinity, S sub n, which also happens to be the sum from k equals 1 to infinity of 1 over k cubed, exists. So whatever this adds up to be, I'm not totally concerned about that in this section. We are concerned solely with just finding some sort of a bound or getting it less than a sequence or a series that we know converges. That will be the game plan for a lot of what we're going to do. But this may not seem like it's in this vein, but it's called the Divergence Test. This test, I didn't know even had a name until recently. The Divergence Test looks like this. If the limit as k goes to infinity of ak does not equal 0, then diverges. So as an example, this diverges since the limit as k goes to infinity equals 1, which is not equal to 0. You can use L'Hopital's rule for this thing. You can divide by k squared, whatever it is your choice is for that. Now, it so happens that this test that I'm using here will tell you if certain series diverge, but it does not give information as to whether a series converges. Let me give you a second example. Consider the series k equals 1 to infinity of 1 over k. This series diverges even though the limit as k goes to infinity of 1 over k equals 0. So here's a series that actually does go to 0. The terms go to 0, but the series does not add up. It does not converge. So the converse, as they call it, of this divergence test is not true. If this equals 0, it does not imply that the series diverges. Let me write that in detail. If the limit as k goes to infinity of a sub k equals 0, this does not imply that the series converges. And in fact, we're going to let S sub n equal the sum of this series, k equal 1 to n of 1 over k. And I'll show you some of the results that I got with my particular calculator. Yours, it depends on the TI that you're using. Some of the TIs won't do these series, but other TIs will. It's not that important here for this discussion, though. I am going to put my n and my Sn values. So when n is 1, that certainly is 1. When n is 10, this is approximately 2.93. When n is 100, this is approximately 5.19. When n is 1,000, this is approximately 7.49. And then when n is 10,000, this is approximately 9.79. So what happens is that the limit as n goes to infinity, S sub n equals infinity. Because the S sub n's are not bounded. These keep creeping up slowly and slowly, but they do keep creeping up. And so while this goes to infinity kind of on the slow side, it will go to infinity eventually. The series of 1 over k is called the harmonic series. From what I understand, it has some sort of a connection to music, but I can't tell you what it is. But apparently there is some sort of a connection to music with this series. Now let's take a look at how we figure things add up and how they don't add up. So let's take a look. I'm going to use this series as an example. So consider y equals 1 over x. And better than y, I'm going to put f of x. Because I need to use this slot here to put my x's and to describe things. All right, what we have then is if you draw a picture of the graph, just a rough sketch, nothing fancy, it has an asymptote of x equals 0, but then it also has an asymptote of y equals 0. Now, let me start by doing a Riemann sum. So I'm going to start at 1, but this time I'm going to do a left-hand endpoint, and it'll look something like this. And then that'll be 2. And from 2, we draw another rectangle. That'll be 3, and another rectangle. that'll be 4. What we have then, and this will go on and on and on until I'll get to here, it'll be like n minus 1 and then n, and keep on going from there and there afterwards. What do we notice about these curves? Well, I do notice that the sum from k equals 1 to infinity, each of these y values here, the height of this rectangle is 1. Then the height of this rectangle is 1/2. Then the height of this rectangle is 1/3. And this one here is 1 over n minus 1, and this is 1 over n. Each of these rectangles has a height. But you can see the rectangles are higher. There's a little bit of rectangle that is more than the curve. So what I have then, I'll do this. I think it's okay. 1 over k then is going to be greater than, I'll say greater than or equal, because when we talk about limits, things could even up there in the end. It's safer to put an equal sign under there anyways. But we already know from the p series, this has a power of 1. We know that this already equals infinity. This does not converge. And here you've got something that is more than this particular integral. So this proves that k equals 1 to infinity of 1 over k does in fact equal infinity. But what this method does is provide us with an interesting test. So let's take a look at a series, k equals 1 to infinity a sub k. Each a sub k is positive. Okay, now next, let f of x be such that f, when you plug in just whole numbers, you get a sub k. So in particular, the series k equals, I'll say 1 to infinity, but it doesn't have to be. But for what we're going to do, this will work fine. So in fact, what happens is this. A sub k is really function values at each of those whole numbers. Okay, then here's what we have. I'll have the summation k equals 1 to infinity of a sub k converges whenever the integral from 1 to infinity f of x dx converges. And the summation k equals 1 to infinity a sub k diverges whenever the corresponding integral diverges. This is referred to as the integral test. And to understand how this works, a picture will be very good. So I'm going to do the same thing I did before. I'm going to start with this series, k equals 1 to infinity a sub k. And remember, a sub k is the same as f of k. So let me draw a picture of f of x. And we know if this has any chance of converging, f of x has got to go, the f of k values have to go to 0. If I am going to, if I want f of x to be continuous, and I think I should do that. Let me throw in f is continuous. Since f is continuous, there's no breaks in this. This is forced to go down to 0 as f of k goes down to 0. It could do weird things in between those k values, but it's forced to go to 0 because of the continuity. Now what we'll do then is I'll graph my AKs. So I'll have k equals 1. I will go up here to the curve. I'm going to make big rectangles at least fatter rectangles so I can sort of label things. And of course this goes on forever, and I'll get out here to n and n minus 1. And so this value then will be a1, or we can call it f of 1, f of 2, f of 3, 2, 3, 4. Let's call this n minus 1. So this is f of n minus 1. And then this is n. That'll be f of n. So we can see that if the summation k equals, I have it backwards, if the integral from 1 to infinity f of x dx equals infinity, then this series is more. So if the integral diverges, then so does the series, because the integral value is less than or equal to the series value. And if this thing is going to infinity, well, so is that. On the other hand, if the series k equals 1 to infinity a sub k converges, then, based on this picture, it's not hard to actually define. I mean, this is pretty good. I can see that the integral's value is less than or equal to the series. Then we'll have an integral that goes from 1 to infinity. F of x dx will be less than or equal to a series that has a finite sum. This will imply that the integral converges. So I have some things. If the integral diverges, then the series diverges. If the series converges, then the integral diverges. Well, let me write something else. Now what I'm going to do is attack the same problem, but with right-hand endpoints. So there's f again. And then when I start at 1, 2, 3, 4, let's go ahead and draw these. I don't do one at 1, but I do one at 2. There's 1, 2, here will be 3, here will be 4, and this goes on and on and on. I'll have 1 over here, where that'll be n. And the heights of them then, we are going to have f of 1, I'm sorry, f of 2, and then the next height will be f of 3, and the next height will be f of 4, etc. And this one here will be f of n. So now, the integral, if I start the integral at 1, I can see that the function itself is greater than the series now that starts at 2. So the integral from 1 to infinity, f of x dx, is greater than or equal to the series k equals 2 to infinity a sub k. Now, if the summation k equals 1 to infinity a sub k converges, then if you add up less terms, this also converges. These numbers are positive, so this is even a smaller amount. Then this converges, and the integral from 1 to infinity f of x dx converges. Now, if it should happen that the series diverges, actually put a 1 here. If that diverges, then this series also diverges because you're just taking away the first term. If this is infinite, taking away the finite a sub 1 is still infinite. So if that diverges, then what we have here is these terms add up to infinity, which would force the integral to be infinite. So in all these cases here, what I've shown that is suppose the series converges right here. If the series converges, I got the integral to converge. So if the series converges, then the integral converges. Because of this, if the series diverges, then the integral diverges. Now on the other hand, what did we do? If the integral diverges, then so does the series. And right here, if the integral converges, so does the series. So basically what we have is f. I'm going to put, it doesn't matter where you start. I could have started at something other than 1. So I'll put from n to infinity f of x dx converges if IFF, the summation k equals n to infinity a sub k converges. So the key here is to start this at the same place that this starts, and you'll be able to do this. And of course, this if and only if means this happens at the exact same time that this happens. They are dependent on each other. One diverges, the other diverges. One converges, the other converges. Well, the first example, let's call this example 2. That converges 1 over k to the p. That's a p up there. Let me change it. Converges whenever p is greater than 1 and diverges for p less than or equal to 1. This is a test here. I should probably have not called it an example, but a test. This is the p-series test. Why is it true that that converges whenever p is greater than 1? Because we know that the integral of 1 over x to the p dx from 1 to infinity converges p is greater than 1 and diverges when p is less than or equal to 1. So it follows the exact same test as we used for integrals. So this is really easy to see. So a series like this, if you look at it right now, the limit of this thing will go to 0 because the bottom has a higher power than the top. But does it actually converge? Well, we're going to take a look at the integral from 1 to infinity of x over x squared plus 1 dx. And you'll do your usual stuff. U will equal x squared plus 1, and du will equal 2x dx. And of course, I have the x dx part. I'm going to divide by 2, and I'll have, when I switch to u, when x is equal to 1, u is equal to 2. Then when x is infinity, infinity squared plus 1 is even more infinity, I suppose. And we have a 1/2 out front, and then I have 1 over u du. Well, this is 1/2 the natural logarithm of u from 2 to infinity, and we already know this goes to infinity. So the series diverges. And usually I'll require this of you on an exam. You need to tell me the test that you used and how you used it. And this is showing me how I used it. So the series diverges by the integral test. So for a while, we're just going to be looking at convergence and divergence and see what happens. Example 4. Suppose we wanted to do the sum from k equals 5 to infinity of e to the negative k. Well, you ought to know that this is going to converge because this is the same as the sum from k equals 5 to infinity of 1 over e to the k power. And then you can use the series for k equals 0, but then you have to subtract off k equals 0, 1, 2, 3, and 4. Fortunately, I don't care about what the sum is right now, so this is not important to me. I'm going to erase it out of there. I just want to know whether it converges or not. So to determine whether it converges, I'm going to look at e to the negative x dx from 5 to infinity. And when you integrate e to the negative x, you'll get negative e to the negative x from 5 to infinity. Well, when you go this route, the infinity, you're going to get the limit as b goes to infinity of negative e to the negative b plus e to the negative 5. Of course, this here, we know that e to the negative b goes to 0. Just a real quick graph of e to the negative x is something like this. It goes down to 0 and rapidly. So this piece will be 0. And so this integral converges. You'll often, I wouldn't say often, but you'll usually, in this book at least, be able to find out the value of this. But that's not necessarily, that is not the value of the sum, almost never. So, so the integral converges. So the series k equals 5 to infinity e to the negative k converges by the integral test. Now, I'll make a note of that. The integral values is not necessarily equal to a sub k. I don't care about those. Not usually. Almost, I'll say almost never equal. I can't say anything more than that because I think there are some times when this integral actually does equal that, but it's very specific in special cases. All right, let's take a look at the next example. Here I'm going to look at k equals 3 to infinity of 1 over the square root of 2k plus 1. And so immediately I'll go to the integral from 3 to infinity of 1 over the square root of 2x plus 1. Well, in this integral, you would let u equal 2x plus 1, then 1/2 of du would equal dx. So I've got this piece covered. This will be u to the negative 1/2, and the dx is 1/2 du, so I'll have 1/2. I'm going to change my limits of integration. When I plug 3 in for x, I'll start at 7, and infinity, twice infinity plus 1 is still infinity, and this will be u to the negative 1/2 du. That equals 1/2 times 2 u to the 1/2, and that's going from 7 to infinity. This will be the limit as b goes to infinity of b to the 1/2 minus the limit, there's no limit here, minus 7 to the 1/2. Well, this doesn't matter because this limit here is infinity. So the series diverges by the integral test. I want to sort of get you used to something too, a feel for when these things are going to converge. Right here, if you ask me, this feels like a k to the 1/2 kind of a situation. And by the p series, they're not going to converge because that p is less than or equal to 1. And notice here it almost identically did become a k to the negative 1/2. It really, literally became that through this transformation. So when I see this, I feel a 1 over k to the 1/2 in me, or in the series, and I immediately know by looking at it, it's going to diverge. Here we don't have a test involving k factorial, but I might try to use, I might try to see if it diverges or not. Let's take a look. What you can do, k factorial, by the way, k factorial equals k times k minus 1 times k minus 2 all the way down to 2, then 1. That's what k factorial is. So it starts at 1 factorial and then goes off. So what you're going to have here is this series k equals 1 to infinity, and you're going to have, I'll take out a k, so I'll get k over k minus 1 factorial. If I take the k away, then I still have k minus 1, k minus 2 all the way down to 1. But now it's pretty clear to me that this series, if you look at, this is k squared, the limit as k goes to infinity of k squared over k minus 1 times k minus 2. I'm going to look at versus the first two terms. I will multiply that out. I'll have minus 3k plus 2. I don't care what you use L'Hopital or something like that. This will equal 1. What that means then is we have k squared over k minus 1 times k minus 2. I probably should have, you know what I should have done? Let me do this. K minus 3. Let me throw the first three terms in there. And then what I'll get in the denominator won't matter after k cubed. So I'm going to write k cubed plus dot dot dot. Well, that doesn't matter now because the power in the numerator is less than the denominator. That equals 0. And if you look at these terms, if you have k squared over k minus 1 times k minus 2 times k minus 3, if you look at just this part, now since this is going to 0, that'll force that to go to 0. So that goes to 0 as k goes to infinity. So by the divergence test, I know that this goes to 0. These terms go to 0. However, I do not quite have a proof that it converges. Unless I can find an integral thing to use on it, or if I knew the sum of this, I don't have a test right now to handle whether it converges or not. So unfortunately, no test yet. The divergence test tells me that while the things go to 0, I honestly don't know whether it converges or not. We have tests in the future that will work with something like this. Let's move on. I'm going to look at 1 over the cubed root of k plus 10. Now I told you, feel it. Feel the series. Be one with the series. This series should feel like a k to the 1/3. And then being a p series, that 1/3 is too small. It's going to diverge. And the way you do it, if you want to give the test to it, which I'll ask you for the test, you can't say that this is like a k to the 3rd series. You have to give me reasons. And one of the reasons will be the integral. So I'm going to replace it with this, x plus 10 to the negative 1/3 dx. I'll leave it to you for this step. But if u is x plus 10, then du is dx, and we end up with, let me see, if I add 1 to this, I'll get 2/3, so I'll get 3/2 x plus 10 to the 2/3, and since I've put x back in, I'll put the original limits in here. The limit, since this is a positive power, the limit as x goes to infinity of this will be infinity. So this series diverges. But I told you, you already had probably a feeling it was going to, because k to the 1/3 is sort of like this series. In fact, if I did the transformation or the substitution correctly and had a u here, I would have u to the negative 1/3, and then you could immediately say it's going to diverge. Let me move on. Here I have k to the e all over k to the pi. Well, if I rewrite that, k equals 2 to infinity of 1 over k to the pi minus e, now it just matters whether this is less than or equal to 1 or greater than 1, and then we'll be able to determine whether it diverges or not. Pi minus e is roughly equal to 3.14159, etc., minus 2.71828, etc. Clearly, this is, I don't know, 0.3 something, but whatever it is, it's most definitely less than 1. So this diverges by the P series test. You can only use the P series test when it's of the form 1 over k to the p. Pi minus e is greater than 1. For this next one, you can almost see the u and du combo that you need to use. So this, if I have an ln of x, then 1 over x is its derivative. So I'll look at the integral. We're going from 2 to infinity, 1 over x. I think I could have did it better by writing as ln squared of x dx. And then we're going to let u equal ln of x, and then du will equal 1 over x dx. So I have the 1 over x dx. This is u squared. Let me plug in my numbers then. When x equals 2, u will be ln of 2. And then as x goes to infinity, ln of x, as we know by now, does go to infinity as well. So I'll end up with negative 1 over u from ln2 to infinity. Well, as u goes to infinity, this piece goes to 0. So limit as u goes to infinity, negative 1 over u, plus 1 over ln2. That piece is 0. I don't care that it actually adds up to ln of 2. The series converges. The series converges by the integral test. And this here probably just put after it less than infinity. A superball is dropped from a height of 10 feet. If the ball always bounces one-half the height of the previous bounce, How far does the ball travel? So the first, when you drop it, it's 10 feet. It bounces, then it comes up 5 feet. Bounces again, it comes up 2.5 feet. So the initial drop, it traveled 10 feet. But then bounce 1 was 5 feet. Bounce 2 was 2 feet, 2.5 feet. Bounce 3 would have given me 1.25 feet. These are the heights they are. But this came down just 10 feet. When it does a bounce and it reaches 5 feet, that's another 10 feet. Then when it bounces 2.5 feet, it goes down, it bounces up, and then back down 2.5 feet times 2. So we've got 5 feet plus 2.5 feet. Well, you get the idea. Can I come up with a series for this? Well, I have the 10 there. Let's see what happens here then. I could go k equals 0 to infinity. I'll have the 10, but then each time I want to multiply it by 1/2 to the k power. Let's see if that actually works and gives me what I want. When k equals 0, I've got the 10 feet. When k equals 1, I got 10 times 5. I've got the 5 feet added to the original 10 feet. That's good. And then when k is 2, I'll have 1/4 times 10 will be the 2.5 that I got there. Perfect. Now, one of the things I haven't said it yet, but I will in a minute, is you can take this 10 and factor it out front because 1/2 to the k is a convergent series. In fact, it's a p series. We know it converges, but we also know how to add it up. Using the formula for this, since it starts at 0, I do 1/1 minus 1/2. 1 minus 1/2 is 1/2. I flip it, and I'll get 10 plus 10 times 2. And that'll end up being 30 feet total. So now I'll write those properties. All the series I'm going to write are convergent. I don't even know. I won't put these because I don't know. It doesn't matter where they start. They all go to infinity. I could put infinity up there for all of them, I suppose, but I'll just put AK plus and minus BK equals the sum of the AK plus and minus the sum of the BK. Of course, everything is convergent here. Keep that in mind. If any divergent series, none of this will perhaps work. Some of it may, but most of it won't. C, if I have a C, A sub k, C is a constant, I can factor the C in front of the series. And then probably the biggest one is A sub k. If you started somewhere at, I don't really care, let's say 1 to infinity, converges if and only if k equals n to infinity of A sub k converges for every n. Sometimes it may be more convenient to throw away the first several terms and just look at what they call the tail end of the series and see what it does. So long as the tail end converges, the entire series will converge, because this is the important piece. This adds from n to infinity, but the first terms, 1, a1 plus a2 plus blah, 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 plus a sub n minus 1, those are finite numbers. That's just a finite sum. So that's going to definitely converge. That doesn't matter. The tail end is important. So keep this in mind and embed this in your brain. I don't know. I'll just say tail end is where all the action is. Located. So to make use of that, I will write the last example here. I have the series k equals 1 to infinity, 2 times 3/5 to the k, plus 3 times 4/9 to the k. And I know when I break this up, each of these series are going to work because I have formulas for these things. I have the sum. I'll even just break it up all in one step. And then I can go ahead and get the formula for the sum. You're going to have 2. The first block here, remember, I'm not starting at 0, so I can't use the formula directly for 0, although I can start it at 0, and then I subtract off 3/5 to the 0, which is always going to be 1. And I'll have plus 3. Same deal as before, since it starts at 1, I'll have 1 over 1 minus 4/9, minus 4/9 to the 0. It really doesn't matter. I have the sum now. I have 2 times, well, 1 minus 3/5 is 2/5. This is 5/2 minus 1 plus 3 times, here I'm going to get 5/9, but I flip it and I get 9/5 minus 1. So I'll have 2 times 3/2 plus 3 times 4/5. So I'll just stop over there. It equals 27 over 5. Obviously, it converges.